Hi, welcome to Chapter 11, Riches in the Rock, which is all talking about all the different materials or resources that we use from the rocks. So as we get started, one of the resources that we're going to be looking at, well, we're going to look at a lot of different resources. Three main categories of resources. The first one is energy resources. Uh, the second being mineral resources and economic resources. And as you can see by table 11.1, we use a lot of material. Now, each of these listed on this table are yearly per capita use of earth resources in the United States. So we can see that we use a tremendous amount of things like stone. Now you may say, wait a second, I don't have a stone, but if we start looking at the global or in the United States, take the total amount of stone being used, and that includes things like roads or public buildings, and then you divide it by the number of population, and that's how we come up with that 9,000 pounds per person per year. Things that we use sand and gravel for is the production of in the formation of concrete, which we also use cement, which is located a little bit further down. Oil and coal, again, that's a per capita use in the United States. Some things that we may not realize that we use as much is clay. We use a lot not only for bricks, but also for ceramics, and a lot of electronics use different types of ceramics. Salts, not just for putting on our food and salting our roads, but in the manufacturing of a lot of goods. Phosphates, we use phosphates for agricultural fertilizer production. Aluminum, you may say, wait a second, that's the 55 pounds, that's new material being used, not recycling. So the recycling is on top of that. So even if you're recycling your cans, we may not, we're still using more aluminum than we're recycling. Then we have copper, 22 pounds of copper, and a lot of electronics use copper wiring. Lead, there's Missouri again. We are a big producer of lead. The Doe Run Company here in Southeast Missouri produces a tremendous amount of lead. Things like zinc for galvanized coatings of materials, as well as the inside of pennies. Then we also have these things called rare earth elements. Lead, we use a lot of lead in lead batteries, even to this day, because it is so inexpensive compared to these rare earth elements here. And so we're using about 1.3 pounds per year of rare earth elements, and a lot of those are in high-end magnets and electronics. So when we start looking at energy production, there's a lot of different types of energy that we're going to be using. We'll classify them in a couple of different categories. The first one is fossil fuels, and we can see coal, oil, and gas collectively are fossil fuels. And we can start looking at this chart, and we can really see that our energy consumption is growing even at this day. We can see that the amount of material that we're using of these resources are increasing, and we use quite a bit of those fossil fuels. If we start looking at these fossil fuels, they are a non-renewable resource, which means that geologists are kept in business primarily by finding more of these resources. Geologists also have jobs working on the environmental sector, trying to clean up some messes that we'll get into later this semester. So here's a map of Missouri from the EIA, Environmental Energy Inventory of America.gov, looking at the amount of energy and where our energy productions are located. And we can see on this map from IEA.gov that we do in fact have in Fulton, Missouri, we do have a nuclear power plant. More on nuclear in a second. Each one of those lines there are pipelines. We've got a number of different pipelines that come through the state. We have some hydroelectric power. I usually get a question about this time talking about the Tomsock Reservoir. The Tomsock Reservoir is not producing electricity, much more it's holding on to. It's like a big battery. Um, at the top of Tomsock Mountain, during times that we're not using as much electricity, to generate electricity, in many of these cases, you turn a turbine, usually with steam power, and then the water will turn to steam, and it'll turn that turbine to generate electricity. So in the summertime, in a hot summer day, we're using a lot of electricity. But at night, we're still having a coal-fired plant. It's still producing heat, but we don't have a need for that electricity. It's not as hot. We're not running as many bits of machinery. So what we're doing at Tomsock Reservoir is we're pumping the water, using that energy to pump water up to the top of the mountain, and then during times of peak need, we'll release that water and let it wash down, and it's still going to turn a turbine, but then we can have that extra amount of electricity when needed, and not necessarily have to build another power plant. So it's a way of basically storing the electricity for a different time, just in the form of potential energy. So that's what's happening there at the Tomsock Reservoir. It's not generating electricity, it's just holding on to that extra electricity. So we've got some other coal-fired plants, we've got some renewable energy plants here, and if we start looking at our next slide, we can see how much energy is being consumed here. And the most recent data that I have is 2018. And so we can see that we're using a tremendous amount of coal, natural gas, ethanol, motor oil, which is, again, all of those top distillate fuel oil, jet fuel, all of these are fossil fuels. If we go down the table a little bit, we've got just over 100 trillion BTUs of energy in nuclear power plant from that one power plant. Then we also are using things like plant material or biomass, other renewables, excluding hydropower. We do have some hydropower, and there's actually a local relationship to this hydroelectric power. As I mentioned, Missouri has a tremendous amount of lead in this area, in the mineral area, and so much when we started trying to switch to electricity to process this, to extract the lead out of the mines, we needed more electricity, and more electricity meant that we needed to find a spot for this extra amount of electricity to come from. And so when the lead company around here was looking for electricity, the electric company around here said, let's dam up a lake, or dam up a river and form a lake, and then they can use that extra water moving down as they release the water that is, again, that stored potential energy to generate electricity. That lake, most commonly as Lake of the Ozarks, and then that relieved the electricity burden across the state, and it was really propagated by the energy demand here to produce electricity for the mining. We can't run hydroelectric, or we cannot run coal-fired plants or oil or gas in a mine because, as we all know, this is consuming oxygen and releasing carbon dioxide, and this would be problematic if you were trying to breathe that oxygen. So everything in the mines around here has to be basically either on a battery, or you produce electricity above and then run an electric cord down, and that's how mining is still done to this day. It has to, we can't operate heavy equipment that runs on fossil fuels in a mine. So when we start looking at other So if we start looking at the total amount just of coal that we're consuming, it's around 675 trillion BTUs. If we start looking at the amount of energy production in the state, how much oil, nuclear power, biofuels that we're actually producing in the state, we can see that we are definitely running on a deficit. We are using way more electricity than we are producing. We do have some coal being mined out of the northern edge of the state, and I mentioned in Fulton, Missouri, we have that electric power, nuclear power plant, and then other places across the state, we have biofuels and solar, as well as hydroelectric. And so when we start looking at the total balance, we have to get some energy from different sources. So if we start looking at these sources, we can see why uranium, or why there has been a push for nuclear power. And when we start looking at the amount of energy per unit mass, we can see that uranium has a tremendous amount of electricity or energy compared to some of the other sources of energy. And so, again, that's 79.5 million joules of megajoules of electricity for every kilogram of weight. And so a lot of power for a little bit of mass compared to something like gasoline, again, almost 80 million megajoules as opposed to gasoline having 46. So we can see why we are looking at those with the appeal of uranium is to the amount of energy. So if we start looking at energy density, it's a clear winner there. Now, when we start looking at energy density, this is just looking at the amount of energy you get, not looking at some of the other issues associated with them. So we'll talk about some of the downsides, but let's first talk about hydrocarbons. Hydrocarbons are materials that are having this hydrogen and carbon, hydrocarbon, ring-like structures that can be combusted in the presence of oxygen to release energy. And so a lot of these are going to be materials that were organic material which was changed under pressure and temperature, usually in the ground under natural conditions. Things like coal, oil, natural gas, petroleum, tar would all be examples of those hydrocarbons. So when we start looking at these hydrocarbons, a lot of these hydrocarbons are going to need to be are trapped naturally in the ground. Now, we've talked about shale, which is made up of clay particles, and one of the unique properties of clay, you may recall I had a poker chip mass looking at this pile of clay that doesn't allow materials to move. They trap organic material. They can trap lots of things in them, and one of the things that they can trap in things like lake deposits would be little bits of organic material. And so this organic debris can get settled in with the clay. The clay doesn't allow any of this material to move. And so if we bury this material, what can happen is the heat and pressure can transform that organic material into a material called kerogen. Now, kerogen tends to be sticky and thick. And so if we heat it up even more, what we'll end up making is oil and natural gas. And if that was the only thing that was happening, is just this heat, this pressure that we talked about in the past couple of chapters, this burial pressure, what's going to happen is that would actually drive the oil and the gas into the upper layers, and ultimately it would go out to the atmosphere and be where microbes could actually break this organic material down. We're going to call that original material that contained tremendous amounts of carbon, hydrocarbons, the source rock. So you need a source rock to trap that material, trap that organic material in. And so if we just had a source rock, as I mentioned, that material, the weight of the overlying rock would actually just cause this material to rise up to the Earth's surface. And so we have some plankton and clay materials floating in this lake or shallow sea. This organic material would then get buried to produce the kerogen, and then we can see that it now is officially called a source rock, whereas if we squeeze it enough that we actually have the temperature and pressure conditions to cause oil formation. And so if we start having this organic material, it would actually move to the Earth's surface. So we need a way to trap this material. And so when we start looking at different places on Earth that we can actually extract some of this hydrocarbons, these are called hydrocarbon reserves. And so when we start looking at these reserves, we can look at the formation, the layer of rock that would be a spot that would hold this material. And in order to be a reserve, we would want to have something that has a high porosity, a high percentage of void spaces, lots of space for those hydrocarbons to fit, and a high amount of permeability. Now, permeability is the ability for water or a fluid to move through a material. And so we want this stuff to be going in and out, no problem. And so something like a sandstone, which would have lots of empty spaces, and those spaces would be very interconnected. So it would be a great hydrocarbon reserve. And so here's the diagram looking at the sample on the right being a really good high porosity, high permeability. Now the one on the left here does have some pore spaces, but the pore spaces are not connected. And as a result, it has a very low permeability. And so as a result, this can be problematic for the migration of this material. And so when we start looking at which of the following of the typical is typical of an unconventional oil. Well, we'll talk about unconventional. Pardon me for a second. Sorry about that. So when we start looking at conventional oil reserves, what we need is a source rock, a place that is going to provide the organic material. Then we need something that would have a high permeability that this material would be able to move through and move up. And then we need a cap rock, something that would actually stop this material from going up to the Earth's surface. And we could even go one step further and say if we had a trap, an area that would accumulate some of this organic material, we'd be even better off yet. And so there's a number of different types of oil traps that we can form. In the previous chapters, we've talked about folds and faults. An anticline is a great area that would act like an umbrella and capture any hydrocarbons moving through the material. And then if we had a layer of clay, what would happen is that clay would accumulate in the middle of this anticline, or the edge of a syncline, but the middle of an anticline would provide a tremendous amount, a great trap of oil. Now, the first oil trap, the first oil pumping that commercially took place was actually in Pennsylvania, hence the name Penn State, or Pennzoil. All different places that are using oil, or that used oil. Drake's well is a famous well that was just about 15-20 feet down, and it was one of these hydrocarbon traps. Drake put his drill in, and the weight of the overlying rock actually allowed that oil to come flowing out, and so he was actually able to use this as a lubricant. And later, as we realized that we could separate out the gasoline from the heavier oil materials, and we could actually use this for combustion. So some of the other oil traps are associated with faults. If we had the ground shearing at that fault, oil and gas can migrate up along that crack until we hit a trap. And then if we have a trap, it would actually hold that material. So if we find these faults, salt is less dense than the sedimentary rocks around them. And so what can happen is it can actually migrate up through the earth or through the soil, deform the soil around them, and these piles of salt rising up are called salt diapares. And what tends to happen in these salt diapares is right underneath on the edges. These are great locations for oil traps. And then we have what's called a pinch out, where one formation transitions to the next if we have a transgression or a regression, or if we had an environmental change where we went from a sandy shore to further offshore. What's going to happen is the reservoir of material, the reservoir of sandy material can die out and be caps on one side or the other with a layer of clay. This would be called a pinch out. And if we find where that sediment pinches out or ends, we could actually potentially find a reservoir of hydrocarbons. Now, when I say hydrocarbons, I'm talking about all of the different types of hydrocarbons, particularly oil and gas. They're found in the same materials. They're both fluids that move. Oil is a liquid state, gas being the gaseous state. So if we wanted to have a conventional oil that had these reserves, we'd want something that would have a highly permeable reservoir that can hold that oil in place. And on top of it, we would need an underground trap, some type of a clay material or a shale that would actually hold that oil from migrating up, or that hydrocarbon from moving up. And if it was too fluid, what can happen is it can migrate out to the edges and make its way to the Earth's surface, and then microbes could break it down, and we would have lost it. So we definitely don't want to have it to be too viscous, because again, too thick, because it has to be migrate. It has to be able to migrate. We'll talk about some of the high viscosity or really thick stuff here in just a second. So how can we find out what's going on in the Earth's, beneath the Earth's surface without actually having to drill? And drilling can get quite expensive. Fortunately, we have developed some amazing tools using seismic reflection. We've talked about P and S waves in chapter 8, where these P and these S waves can travel through different materials and reflect back. And so if we have a series of seismometers, we could actually pick up these seismic waves, and we can actually generate these seismic waves with these giant machines called thumpers here. And they literally will smash the ground and shake the ground around them. And what can happen is that ground shaking can generate these P and these S waves that are moving through the Earth, reflecting off of each layer, and giving us a seismic image of these different layers. And if we found an area that would be conducive to a trap, that would be a great spot to try to find some oil. Now, if we were drilling down into the Earth, we traditionally would just start digging a hole with a drill, and that can be quite dangerous, because as we already mentioned, the deeper you go, we have this rock pressure. This rock pressure is pushing in all directions. If we allow a place for that oil to come shooting out, this can be quite dangerous to the person operating the drill at the top, because this oil is under tremendous amounts of pressure, and it can be it has been known to kill the derrick operators. So to alleviate this and make this a little bit safer, what we've done is we've used a local sample. Now, you may have heard around here a sample of material called TIF. TIF is actually the mineral barite, and barite is crushed. It's a very soft material, but it's known for its high specific gravity. It has a really heavy for its size. And so what we'll end up doing is crushing this material and putting it as a drilling mud behind the bit. And so this bit will crush the rock around there. It'll scrape the material and it'll carry the rock out through the tube. But on either side, we're injecting some of this drilling mud and backfilling around the well casing. And so this is going to keep this oil much more confined. You may have heard about the Deepwell Horizon in the Gulf of Mexico. What happened in that case is after we found some oil, instead of coming straight up, they typically will back this out, create a little box that will create a layer of material. Then once the the bit has been removed, then they can open up this derrick and allow the oil to come flowing out. Remember, the weight of the overlying rock in many cases has actually caused that oil to migrate up on its own. We can later pump this oil to get even more of this oil out, but that's unfortunately what happened in the Gulf of Mexico. Instead of shearing off the top and holding the oil in place, it didn't cut all the way across and the backup system failed. So as a result, that oil was coming out until we could actually drill back in to that tube and fill it in with more drilling mud, more barite. And so holding that material in place. And so barite, this drilling mud, plays a huge role in the production of oil and the safety of the production of these hydrocarbons. Now, in the past, we're able to drill straight down, but later we've developed some new drilling technology, which has been really, really useful at drilling and increasing the production of these oils. We've now can drill, instead of drilling straight down, we can drill at an angle. And if we start drilling at an angle, we could actually start to hit the area that, even if we didn't hit that middle of that anticline perfectly, if we found that source rock, we could potentially drill sideways and extract out some of these oil. And so commonly what we would do is drill one, drill back the other way, drill back the other way, so we can actually get oil from lots of different locations around here and get more oil. Instead of having to drill one well down, if we drill to the left, to the right, to the north, to the south, to the east, to the west, and anything else in between, this can provide more efficiency from these wells. Additionally, since we've already mentioned, sedimentary rocks are typically washed downhill. So one of the places that we accumulate a lot of this organic material is in shallow ocean water. And so if we have areas that are still underwater, we're going to have to create a drilling platform to extract that oil. And so here is an oil platform. The tankers will line up and accumulate the oil. Once we've accumulated the oil, they'll move it onto a boat and then they move it back onto shoreline for processing. To process oil, what they end up doing is they cook it. And just like if you were distilling alcohol for alcohol drinking alcohol, or rubbing alcohol, what we end up doing is we heat up all of these oils, and if we heat it up to a different temperatures, what's going to happen is these oils will start to separate out in what's called a distilling tower, and it'll separate out the heavy stuff like tars from the gasoline, which is the vast majority of it is, and then the remaining material is a higher octane rocket fuels, and then we can actually capture some of those natural gases as well. And so this needs to be done before we can actually use a lot of these oils. So that's being done. There's a lot of these right along the Gulf of Mexico, where we're separating out the refining the oils. After we've poked a hole into this source rock, in some cases the oil will come flowing out under its own under hydrostatic pressure, but in other cases we can coax a little bit more out by using these oil derricks. And so the head of this pump is going to go down, it's going to pump this material out, and so this moving back and forth, you may see these oil derricks moving back and forth, pumping this oil out, storing the oil in a storage tank over here. And so then you could bring a truck into the storage unit and extract that, move that oil back to the refinery. And so I mentioned a truck. If you had a sizable amount of oil, you could actually just keep a pipeline of this material going down. And so in the Alaskan Transatlantic pipeline, this area is where these tankers are moving this material. There's been talk about why not put it underground. This is an area of permafrost, and so keeping it above ground would be easier than putting it into the ground, trying to cut through this permafrost. And if it got cold, it would actually become more viscous or thick and be a more difficult time flowing through this material. Other things that we can move to carry this material is through big boats or oil tankers. And so we can see that these oil tankers are quite huge. And so one oil tanker is enough. It can carry, and your book talks about carrying 1 million barrels of oil in one container, enough to supply the United States for a few hours of oil. And so we have to keep these oil tankers moving if we want to have transported this oil so the refineries can keep in production, and we can keep a strong supply of oil. So when we start looking at conventional oil, we can get about 30% of the hydrocarbons out of a formation using traditional methods. But we can also use secondary recovery. One of the examples of secondary recovery is hydrofracking, where we'll actually crush the rock. We will inject this. We will use that horizontal drilling method. Then we will go in and detonate some explosives and some sand. And once we extract that sand, inject that sand and potentially a lubricating agent, we can extract out oil, both in old wells that we've already can't get any more production out of through using traditional methods, as well as we can actually look at other sources of material. And so these sand, what needs to happen, again, horizontal drilling. We need to frack that material with an explosive or high pressure, and then if we just did that, it would close back up without allowing that oil to be liberated. So what we need to do is keep those pores open. And so one of the ways to increase the porosity is to use a frac sand. Now, here in Missouri, we do produce some of the frac sand. There's a lot more production up in the Great Lakes region, where we have some glacial material that had a high amount of silica-rich sand. And so each well in production, on average, it's 10,000 feet of horizontal well in 2010. And each one of those wells would require 2,500 tons of frac sand. So we need a lot of frac sand to make these wells viable. And so There's a couple of different locations where we've used either both traditional wells as well as the unconventional oil reserves. So if we start looking at where we have these oil reserves, these are areas that are very much confined to flat, old reef structures or areas that were accumulating this organic material. And so if we start looking at where we have a lot of oil on Earth, we can see here in the United States, we've got the Permian Basin, an area that used to be underwater. We've got the Gulf of Mexico, which some of it is currently underwater. We've got the North Slope of Alaska. And then the big one, the area that has the majority of the world's oil is this one area known as the Persian Gulf. And you can see that region. So when we start looking at the distribution of the oil reserves by country, and again, these are traditional oil reserves, how much oil we can actually extract out currently. We have about 808 billion barrels of oil in the Middle East, as opposed to North America, both the United States and Canada. That's only about a quarter of that, 220 million barrels of oil. Now, there are some additional oil that we can get out of rocks, but not through the traditional traps. We have things called oil shales, tight oil and gas, as well as tar sands. Now, the tight shale or the tight oil and gas occur in the source rock themselves, and so if you do this fracking method, you can actually prop open the cracks and extract the oil that way. There's a concern, and your book actually talks about some of this concern because each one of these fracking agents, these areas are going to crack, and there's a potential for some of that organic material to make its way into the drinking water. Additionally, each company has its own proprietary blend of chemicals which help liberate that and loosen up that oil off of the shale. And so the concern is that lubricating agent can potentially get into the drinking water. And there's not since it's a proprietary blend, the oil company will not release what is used as that lubricating agent. And so there's a struggle between energy consumption, which we already established that we use a lot more oil than we consume here in Missouri, with the safety of the drinking water. And so the struggle is still occurring to this day, and there's lots of different views on this, whether the cost-benefit analysis works out. And so if you'd like to know more about that, by all means, I recommend looking at some of the different resources, particularly the book has some of these resources, as well as the various websites like the EPA has commented on these. Here in Missouri, we don't really have to worry too much about these hydrocarbons because we don't have any. There are two major oil shales that have been in the past that we've used, as well as a third one that is coming on to play. The first one is the Marcellus Shale in the northeast part of the United States. The second one, about 10, 15 years ago, really came on strong in North Dakota, the Bakken Shale. And then the third one down in Texas is a third potential shale deposit going Texas and into Oklahoma. So if we look at the unconventional oil reserves, these are where the hydrocarbons are locked in impermeable rock that we have to figure out a way coax that hydrocarbons out of that impermeable rock. So when we start looking at these hydrocarbon reserves, they can be in a lot of different locations. The oil shales, the shale oil, shale gas. Again, those shales don't allow fluids moving through them very easily. And then we also have tar sands. Tar sands are also hydrocarbons, but in this case, we have some really thick, high viscosity materials. Usually, the tar sands are associated with being viscous because of an additional amount of sulfur in that oil, in those hydrocarbons. And so you hear about the price of light sweet crude. Sweet portion of that talks about how much sulfur you have. If you have sour crude, and that is a thing, it's not worth as much because you have to extract out all this excess amount of sulfur, making it much more thick. And we have this accumulation of excess amounts of sulfur. So these tar sands are vast deposits, but again, it's too thick to use pumped through the ground. So we have to coax this out by stripping away, taking the entire unit of rock and have this open pit mining. And then we'd have to heat up that sand where you could lower the viscosity, make it a little bit more runny, and then you could separate out the sand from the hydrocarbon. And so we can see once you have that sand, you would have to have that oil. You still would have to, it would be sour crude, and you'd have to remove the sulfur from that. When we start looking at coal, just like the Middle East had a tremendous amount of oil, we have here in the United States a tremendous amount of coal. Going back to the last couple of chapters, we've been talking about the Carboniferous period. During that Carboniferous period, we were accumulating tremendous amounts of coal. And so I've heard it said that we have about 500 years worth of coal. And so coal is formed when this organic material, mainly woody plants, die and fall into a low oxygen environment, basically a swamp. And so this organic material would start to get buried, and if it's buried, then it can't get it can't break down. And so these would be definitely found in swamp environments, freshwater swamp environments. And so we'd start off with a swampy environment depositing this stuff called peat. And so this is plant material. In some cases, you can actually see the woody material itself. You can actually some cases see rootlets and things like that, where it's just organic material. And the lighting is, I don't know if it's working out, that it's actually more of a brown than it is a dark brown as opposed to black. And so what happens is this coal gets squeezed, and every time you squeeze this coal, you're going to increase the amount of carbon per volume. And so the next coal that we have is something called lignite coal. You can see it's a little bit darker. In this case, it's clearly black, and breaks apart fairly easily. The next type of coal that we would have is subbituminous and then bituminous coal. So when we start looking at this bituminous coal, it tends to be shinier, higher increase in BTUs. And then finally, the last type of coal almost looks like obsidian. It's a sample called anthracite. It's a metamorphic sample. Really, really high amount of BTU per unit volume. And so it's the highest energy density that we're looking at here. And so which one has the highest is that anthracite. Obsidian, well, it looks like anthracite, has no carbon in it. And so when we start looking at anthracite coal and bituminous coal, we can see that we have some very large amounts of coal around here. Southern Illinois has a fairly high amount of coal. Unfortunately, one of the downsides to some of this coal is it can contain sulfur, and so you have to remove the sulfur, and otherwise you're ending up putting that sulfur into the atmosphere when you burn that coal. If we start looking at some lower energy coal like lignite, we have a tremendous amount out in the western part of the United States, like Wyoming. And so a couple of different methods for removing the coal. One of the methods is known as strip mining, where you literally strip away the soils, get to the coal, and then remove that material, or put that material back in place. And so this is strip mining, hence the name. In other cases, we can use a drill to go underground, and this area is crushing up the sample, the concern there is that some of this methane gas is, if we don't ventilate, again, since you're trapping in organic materials here and you're cutting through organic material, one of the problems you may have heard about the canary in the coal mine is methane gas can build up. And so this methane gas would kill the canary, and so it could be a sign of things to come if you didn't get out of there or get ventilation in there. And so some of the other problems when you're crushing up this rock is that little bits of dust particles can get into the air and into the lungs. And you can see this person has a respirator on to not get black lung disease or silicosis. Silicosis occurs when you are crushing up these little bits of organic material, and we get little bits of chert in there. And so it could crush up this chert and again, cause some irritation to the lungs. So those are non-renewable energy sources, and we are currently using more fossil fuels compared to any of the other energy sources. And so when we start looking at the, you may have heard about something called peak oil, where it's a non-renewable resource, which means that we're using more of it than and we're not really producing any more under a human time scale. And so as a result, the price of oil is going to, the amount of oil that we're going to, the amount of hydrocarbons that we're going to get is eventually going to run out. And so when is that lack of production going to occur? And so it's directly related to the price. If the price goes up, we might be able to find lower and lower quality, but it wouldn't be cost effective. And so at that point, we want to switch over to a different resource. Some of the other problems that can occur associated with hydrocarbons is oil spills in the production. And so since we've already established that we can carry so much oil in one of these big boats, if one of these boats should break, this could create a huge problem. The Exxon Valdez is a famous example of one of these. When you start dealing with coal, again, a lot of this coal contains sulfur, and so this can create acid mine runoff. In some cases, if we are producing these fumes, if these fumes catch fire, if coal catches fire underground, it can actually continue to burn, and you can actually burn an entire seam of rock underground. And so you'd have these areas that you can't mine anymore, and it's releasing these toxic fumes. And so that's obviously a big problem. The release of carbon dioxide and nitrous oxide from coal can rain down rain that has a lower pH. We call that acid rain, and again, usually associated with coal power plants. One of the ways that we can end up reducing the amount of acid rain is to put in what are called scrubbers, which are basically limestone. It'll create a chemical reaction bonding with that sulfur and releasing less of that sulfur into the atmosphere. These scrubbers have to be replaced every so often. And so that is one technique that we can reduce the effects of acid getting into the environment. We can also, burning carbon dioxide, as we already know, is a greenhouse gas, or excuse me, burning fossil fuels is a it releases carbon dioxide, which is a greenhouse gas, and that can lead to changes in the environment. More on that in chapter 20. So those are all hydrocarbons, and again, we talked about some of the negatives of those. I mentioned nuclear power plants using uranium at the beginning of this chapter, and so when we start looking at uranium, it has a tremendous amount of energy resource. Now, we do have some uranium deposits here in Missouri that we can actually extract out and generate electricity by turning a turbine, having nuclear fission. You turn the uranium, as it breaks down, it'll give off a tremendous amount of heat, which will turn water into steam and turn a turbine. And so negatives, the positive is a tremendous amount of energy with a little bit of material. The downside is that these reactions can run out of control, and when the uranium has been spent, the spent rods, we have to find a place to put these spent rods. And so some examples of some of the meltdowns that have occurred in the past, the Fukushima power plant after the after the earthquake and tsunami. It led to a meltdown of a nuclear power plant. Chernobyl is another one. And we nearly had one here in the United States on 3 Mile Island. We were able to turn the power plant off, but we still don't have a really good place to put the radioactive material after the spent rods have been used. There has been talk about putting it into Yucca Mountain in Nevada. That seems to be stalled for the last 30 plus years. There is one spot that has some radioactive waste. It's called WIPP in the western states as well. The WIPP did have a problem that we'll take this radioactive material and encase it in the past, we've used silicate material that was crushed and super absorbent, and we kitty litter. And so there was, unfortunately, we switched over, whoever was running it didn't read the ingredients on some batch of kitty litter that they purchased, and they used organic kitty litter that didn't have the silicates, but it was wood fibers. And so it didn't turn into a glass and encapsulate the material. And so it led to the WIPP needing to be shut down and sealed off in that sector. And so, again, trying to figure out what to do with all this radioactive waste that we're producing probably should be considered a little bit before moving forward with additional production of these radioactive power plants, these nuclear power plants. And so that is, again, big benefits and big rewards when we start dealing with this radioactive nuclear uranium, which turns into power plants. We've had a strong rise in other forms of energy, harnessing the Earth's, these are known as alternative fuel sources. The first one is being geothermal energy. If we are close to an area that has a high amount of high geothermal gradient around places like blobs of magma or batholiths in the ground, if we drill into this region, we have water turning to steam and releasing this power, and the steam coming out can actually generate electricity. And so if you're in a place like Iceland, this is a great energy source that you have. 80% of their water is basically just running through there, so they don't have to heat up their water or heat their homes with an extra energy source. They can just use the earth itself. We can't use that here because we don't have a high enough geothermal gradient. And so you'd have to go to a place like Yellowstone, but that's a national park, so that one's out. Places in Southern California, there are some places in California that have some geothermal energy. And so there are places that have this as an energy source, but you have to be near the internal heat. source. Here in Missouri, we do have a couple of rivers that we have dammed up for using the potential energy of a river to generate electricity. The downside is that the reservoirs can fail, these dams do have a real big impact on the river itself. There was a push in the 1970s to have another lake being put place on the Merrimack River just outside of St. Louis. That ultimately was determined not to go forward with, but that was a big proposal again, as another energy source for the people of Missouri. Wind energy is generating electricity through wind turbines. Again, this is one that is not using water, but it's simply using wind power, the uneven heating of the earth to generate wind that is already occurring, and then capturing some of that wind energy with a propeller, and that's turning the generator as opposed to using water. And then finally, solar photovoltaic or solar energy. So let's look a little bit at some images of these. Geothermal, again, poking a hole into the ground and capturing that water under pressure and turning that into steam. The upper image there is an image of a nuclear power plant, turning that water into steam. Now the water that is being directly exposed to the radioactive rods is a closed loop, but that hot water comes in contact with that's turning the turbines is cooled off by additional water that will be released into the atmosphere, but it's water vapor. So as long as this is a confined unit, as long as this side's a confined unit, it will not be exposed to the atmosphere. Again, we have a hydroelectric power this is an example of one of the largest dams on Earth, the Three Gorges Dam, something like a mile wide by 900 feet high. It's a huge, 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 huge dam, and can generate a tremendous amount of energy on any of these hydroelectric power plants. Again, some of the downsides is the dams can fail, as well as the impact on the river, the temperature, the salinity, the temperature, the sediment load. More on that in the chapter on rivers. Wind power, as this one is accumulating using these fan blades to turn a turbine. And then we also have photovoltaic cells. This is turning light into electricity. And so what happens in the photovoltaic cells, the sunlight is moving electrons from one side of the photovoltaic cell to the other to generate an electrical current. And so that current is great when the sun is out, but we do need to store some of that energy because we have night and cloudy days where that sunlight is not generating electricity. So we need to have a good battery if we wanted to use this on a regular basis. So which one of these is which energy source is using photovoltaic cells? There we go. It's the electricity using solar energy. So I focused a lot on energy resources. The rest of the chapter is dealing with some of the other resources. Metal is something that we use a tremendous amount. Now, native metals can be mined straight out of the ground. Other metals usually are oxides, sulfides, and sulfates. Again, those metals that are bonded with oxygen, sulfur, or sulfur and oxygen have to be smelted out, have to be driven the sulfur or the oxygen off to generate that metal. And so The image on the left is our state's mineral. It is a sample of galena, and we have tremendous amounts of this lead sulfide. And then we have an image on the right there is malachite. It's copper, carbon, and oxygen. And so you have to separate out these materials. Now, an ore is where we have a rock that is a high enough concentration to be worth mining. And so there's a lot of factors. So what's the price of that mineral resource? How much of that resource do we have in the rock, in that unit, and how costly is it to extract? So around here, we are, if we have the Bonne Terre Formation has a, if the grade is, I believe the last time I spoke with one of the local mining companies, they said if they had about 8 to 11% galena in a late formation of rock, they could process it it wouldn't cost them any money to extract that galena. They could break even. If it was higher than that, or if they could get more galena out, or if they had other secondary materials in there, it would be worth mining. But if the price of galena should drop, or if the energy costs go up to produce these mines, if the layer went deeper into the earth, that it required more resources to extract, it may not be a ore. I was told around here that, well, I do know we have cobalt around here, but during one of the world wars, we did not want to rely on other nations to have for our cobalt. And so as a result, we artificially inflated the price of cobalt here in the United States to make it worth our while to process the cobalt around here. As we're using more of these metals, economics have changed. And a survey was done last year in 2019 to potentially go and mine some of these cobalt resources again. So again, economics play a big role in whether a rock is an ore, the concentration of that metal, and what are the costs of mining. All of those have very little to do with the sample itself. You could have a sample itself go from being a resource to not being a resource to being a resource again, and it had nothing to do with that sample itself. Again, what is the demand for those resources? And so they form in a number of different circumstances. You will recall that Bowen's reaction series had different minerals that were forming at different temperatures. And so some of the leftover things that don't fit well into Bowen's reaction series are things like gold, silver, copper, mercury, lead. And so those samples, if they were in the magma, they're going to get higher and higher and higher in Bowen's reaction series, and they're going to get basically on the edge of the igneous rocks, as is the case with the Black Hills gold. And so if you wanted to find things like gold, silver, copper, mercury, and lead, unfortunately, our blob of magma here in the St. Francis Mountains didn't have any gold or silver, very little silver. It had a lot of lead. If it had different resources, we would be mining different resources at this time. But so if you wanted to find a lot of these gold, silver, copper, mercury, and lead, look on the edges of blobs of magma. If we have hot water moving through the ground, it can actually dissolve different minerals and then precipitate them out in a different location. One place that we have some of these mineral resources moving through the water are at seafloor sulfide deposits. So again, here's these blobs of magma. As Bowen's reactions series is precipitating out different minerals, this chemical fractionation can start to separate out these different materials. And so a lot of times we'll find these on the fringes of the blob of magma. So what we're having here is the hydrothermal, where the water is moving through, it's separating out, it's concentrating the ore materials on the edge of these magma sources. Seafloor massive sulfide deposits. And we have a lot of these black smokers at the mid-ocean ridge. And so these are in open water, and so international waters. And so there's been a lot of push to try to figure out who owns these mineral resources. And so again, sulfides are sulfur plus a metal. And so these are tremendous chimneys of sulfate minerals. We talked about the banded iron formation a couple of chapters ago when we started having microbes that were producing oxygen and putting oxygen into the atmosphere. The oxygen then precipitated out in with the iron to create the banded iron formations in places like Michigan, precipitating directly out of water. When we start looking for deposits, since minerals have different densities, one of the ways to find things like gold that have a high specific gravity, a high density, so these materials will wash out, and in some cases, we can find them in rivers. Rivers are great at sorting out different metals. And again, I think I've mentioned using a pan in a previous chapter. When we start looking at residual deposits, these are minerals that are formed or left behind in the weathering process. So we talked about in our chapter on weathering and sedimentary rock, we form these soil horizons. And if we start washing out some of the minerals, it can leave behind other minerals. And so we can have concentration of minerals. And so bauxite is a classic example of this aluminum ore, which is concentrated in the E horizon of the soils. So when we start looking at mining, there's a lot of different mining techniques. The first one that they're looking at is open pit mining, where you're extracting the entire unit of rock, and then you crush the rock down into smaller and smaller pieces that you have either the mineral that you want and the leftover material. The leftover material is called tailings or chat around here. And then the other material that you are removing is the ore. And in this case, they're cutting steep walls and with some steps in there to ensure the mine's safety of these open pit mines. Again, these can get quite large. We have underground mining, where you find a little unit of rock or a shaft that would be drilling down into. And we did a lot. We started with actually open pit mining here in Missouri to mine our galena in these pits. And then we found these units of rock that had this material, and we went underground. And so in Bonne Terre, we have our entrance to these mines, and we continued down, and that underground mine extended through Park Hills. It died out before we hit Farmington, going down 67, but that area from Farmington, or from Bonne Terre to Park Hills, is a tremendous amount of underground tunnels, which are still there. I believe I was told that there was 350 or so miles of underground tunnels, so enough to go from Park Hills all the way up to Chicago in underground channels. So when we start looking at the rest of the materials, the non-metallic mineral resources, these are not metals, but we still use for a lot of different, we're still mining from the ground. Some of these are things like dimension stone, stones that are used like had granite countertops would be an example of a dimension stone. And then we have crushed stone and concrete, which we use as an aggregate. So here's a building stone, just as it is, as well as things like marble, limestone, granite, which we're cutting and polishing, or cutting and using for um, various applications. So when we start looking at a non-metallic mineral resource, that would be something that we'd be using the mineral for. And so which of these is a non-metallic mineral resource? Well, bauxite is a metal. It forms aluminum. Galena, a metal. Coal is not a mineral, so the answer would have to be marble because it is a mineral resource and it's non-metallic. Oh, there's marble right there. Here's some examples of some of this crushed stone where they crush up this rock, used for the manufacturing of concrete, cement, and drywall. Gypsum being drywall, concrete and cement, both using limestone. One has been, you throw the limestone into a kiln to make that cement. All right, any questions, be sure to let me know.